Hi, my name is Kulin Seth. I work at Apple in MPS team, and today I'll discuss enhancements made to the MPS backend in PyTorch. So let's get started. So I'll go over the qualification of MPS backend to the beta stage. New features we have added, such as the profiler support, custom kernel, and developer APIs to the MPS backend. And we will close out with some of the performance improvements made to the MPS backend since our release last year. Now, starting with the beta stage. Just to recap, MPS Backend started its journey with PyTorch 1.12. Last year, when we introduced the GPU-accelerated PyTorch on Mac platforms. Since then, multiple improvements have been made for optimizing the memory usage and view tensors. This year, with PyTorch 2.0, the MPS backend has been qualified for the beta stage. Now, what that means is we have support for top 60 most used operators and more. The testing coverage has greatly improved, and the network coverage has expanded as multiple popular models adopted the backend as their default backend on macOS. But these were not all the improvements we made. There is support for new features available in the latest PyTorch builds, and we are constantly making progress on it, such as profiling support, custom kernel, and some of the developer APIs, which I'll go in more detail later. And furthermore, the developers not only adopted the PyTorch MPS backend in their external networks, but also have contributed code for many new operators into our code base, such as histogram, group norm, sign bit, pixel shuffle, and many more. Now let's discuss some of the new features added to the MPS backend. Starting with the profiler support, which was enabled using OS signposts, which is a feature in our OS. It highlights operations which are executed on MPS backend, blitz between CPU and GPU, and some of the operations which fall back to CPU. To use Profiler, your application, we have a simple example which I'll go over, and some of the API needed to enable that support. It has been integrated to the Metal system trace, and there's a command line tool which is also available for developers to take a look at. Now let's look at a simple sample network, which uses a sequential model composed of linear layers and soft shrink activation functions. Now this is a strawman example. You can implement it directly as an op in PyTorch, but I'm going to use this as a way how we can profile it if it was not available as a backend op. What we can do is that we can use the start and stop APIs, which we enabled in MPSProfiler, and have different modes to capture the signpost information as shown below. So what happens as a result of this, you get a system trace which uses all the OS signpost information after enabling those API, and it can be visualized using a tool called Metal System Trace. It has a lot of other information, along with the fact that whatever the signpost which we had enabled as part of the PyTorch is also represented along with the other things in the timeline. So here it highlights like the blit calls shown in the top. You have fallback CPU kernels, so the things which didn't actually got accelerated on MPS, and operations which were actually executed on MPS. And it allows you to actually start introspecting your network. Now, as you can see here, the soft shrink, at this point when we captured it, was falling back to CPU, which is very slow. Just as an aside, for developers who would like to quickly look at which operations the application is spending most time in, we also have a facility of command line tool. As shown, using an environment variable, you can dump out information about each layer, such as the data types, shapes, GPU time, and it allows you to introspect their application quickly. Now, continuing with our example from before, we saw that the soft shrink was falling back to CPU, which leaves a big gap in the GPU timeline. Now, to improve the performance, we'll go over some of the custom kernel support we added, which is one of the ways to do this. Now, there are 3 steps to write a custom operation. You first implement the operation in Objective-C and Metal. You create the Python bindings and build your extension. And finally, after your extension is built, you can import that operation into your application and begin using it. So let's start with the operation implementation. There's a lot of code, but I'll go over from the top. So you start with importing the Torch extension header, which includes all the PyTorch bits to write the C++ extension. Now, after that, there are APIs which we have exposed to enable the custom functionality. So you have this get command buffer MPS Backend API to get a reference to the MPS stream command buffer. Now, this is the same command buffer we use in the backend to encode work onto. So the work you are doing is as same as, and it's a first-class citizen as what we are doing work on. And this enables to use optimizations like commit and continue to reduce the CPU side overhead, which was discussed in last year's talk. Also, we have this get dispatch queue API to get a reference to the serial queue. Next, create an encoder using that command buffer which we got a reference to, and it allows you to define your custom GPU kernel on that. You encode the kernel using the dispatch queue to ensure the submissions from multiple threads are serialized. After all the work is encoded, you use the synchronize API to wait until the command buffer is done. Or if you don't need serialization, you can use the commit API. And this allows you to internally use commit and continue. Now moving forward, in the second step of the custom kernel support, you can use the PyBind 11 to bind the Objective-C functions into Python in a similar manner, so in a simple manner. Next, using the CPP extension, you can build the custom soft sharing library, which can be included in your application. So as a final step, the custom built library is ready to be used in your application. And we have replaced the soft shrink, which was earlier slow and falling back to CPU, with your customized MPS shrink library. Now, with the newly added custom kernel support, the model runs much more efficiently. All the copies and the intermediate tensors created by the fallback to the CPU are gone, and the sequential model runs much faster. Here are some of the additional APIs on events such as record, wait, and elapsed time to do event management and create custom timing operations. Moreover, APIs on the MPS allocators, such as set per process memory fraction, exposes developers much more fine-grained control over the backend for memory operations. Finally, to wrap up this talk, let's go over some of the performance results. As you can see, the MPS backend has been significantly optimized. With PyTorch 2.0 and macOS 14, the MPS backend is up to 5x faster compared to our initial release across various benchmarks from TorchBench. That's it from me today. Thanks for listening, and have a great conference ahead. And if there are more questions, I'm available, and please reach out. That's it. Thank you.